So first of all, remember a function is something where you have one output for every input, all right? So remember we've done the vertical line test, where as long as you can draw a vertical line, it only crosses once, then it's a function. That means you only have one output for every input. So one y for every x that you put into it, all right? And so now that we've done basic functions, we are going to do function operation, meaning we're going to add, subtract, multiply, divide functions, all right? They give you an example. They have this first function f, this second function g, and they've given us the actual functions here, x plus 1 squared, x minus 2. When you have the function and then parentheses, what they mean is they want you to plug this number in for the variable. So if I want f of 4, I'm going to put 4 into the function. 4 plus 1 is 5. 5 squared is 25. That is the output of f of 4. G of 4, that means input 4 into the g function. So if I put 4 in, 4 minus 2 is 2. The output from the g function is 2. So you can add and subtract functions. You can do it after the fact. Input, input, add your two outputs. Your answer is 27. You can do it before the fact. You can say, well, x plus 1 squared plus x minus 2, and then come up with a new function. FOIL it and combine your like terms, and then plug in 4 once. You will also get 27. And so these are the operations we're going to be doing with functions. We're going to be doing basic operations, but now it's going to be between functions. So as you do these basic operations, you're going to be adding functions. That means you need to remember like terms. Those are the only ones you can add. We'll be multiplying functions. That means you need to remember your properties of exponents. When you multiply variables, you add their exponents. And so we're going to be pulling in some of the stuff that we've been doing with the past about functions. So let's look at this first example. They've given us the example that they used there, x plus 1 quantity squared and x minus 2. These are the two functions they've given us. And now they want us to do these operations. You'll notice they actually don't want to put any number in. They just want us to come up with a new function that represents this particular rule. So we are going to do what I showed you a little bit there. We're actually going to work it out. They want us to add the two functions. Well, if I add the two functions, I have x plus 1 squared plus x minus 2. This is f plus g, based on the functions that they gave me. Now to simplify this, I have to do my basic operations here. So I have to do my exponent. Well, that's x plus 1 times x plus 1 plus my x minus 2. So to do this, I need to FOIL. So I have x squared. I'm going to get 1x and 1x, so that's 2x, and then 1 times 1 is 1. This doesn't have any number in front of it, so I just have to get it out of the parentheses, x minus 2. My final step here is to combine any like terms. I have x squared. It doesn't combine with anything. I have a 2x and a 1x, and I have a 1 and a negative 2. So this represents what happens when I add f and g of x. That is my new function that represents the sum of those. You would do the same thing with subtraction. You would basically get to this point, this x squared plus 2x plus 1 minus x minus 2. With subtraction, what do you think you need to watch out for? This little guy right here, okay? So remember to get it out of the parentheses. Here, it wasn't an issue because we had just a plus 1. Here, that negative applies to the entire group. So it's going to be x squared plus 2x plus 1 minus x plus 2. You have to distribute your negative there. And then again, combine your like terms. I have a 2x and a negative x, and a 1 and a positive 2. And so subtraction would look like this. Multiplication. Multiplication takes those two and they multiply them. Again, we can start from where we've already FOILed it. If I have x plus 1 squared times x plus 2, I'm going to do something like this, and I'm going to distribute. Distribute my x through, distribute my 2 through. And so once we've done all of this, we can combine our like terms. All right. X cubed doesn't combine. 2 and 2. That's is that a minus 2? Yeah, that's a minus 2. So 2 and 2x squared. Those will cancel. This is going to be a negative 4x. Negative 2. All right. So you're doing basic operations with these. You're just, whatever it tells you to do, you're going to do. With division, there's not much you can do other than just put them on top of each other. So if we have division of these, I would just say x plus 1 squared over x minus 2. That actually doesn't simplify. The only thing I have to do with division is I have to make sure I give a little bit of a statement over here. Why would I need to say that statement right there? Why would I need to specify this? I didn't specify it for anything else. Why here? Why can x not equal 2? Yeah, the reason you have to state this, and this is division that you're really going to have to pay attention to. The reason you have to state this is it can't equal 2 because you can't divide by 0, okay? So you'll notice that I did not put any little extra pieces here because x could be anything I want. That is a continuous function, all right? But think back to when we did functions and when we did domain and range and things like that. We have to specify, yeah, this works perfectly fine, all but one spot. It's going to work everywhere except for at 2. All right, at 2 we have a problem. We can't divide by 0. So this is the answer except for this one number. It doesn't exist at that one number. All right. If you look at this one, when we added the two functions, so f of x was a parabola. Remember, an x squared is a parabola, shifted over 1. G of x was x minus 2. X minus 2 is just a line that has a y-intercept at negative 2, all right? But when we added those together, you know, it looks like it is still a parabola. The reason it is, if you look at your answer of those two from our example, you ended up with a final answer that had an x squared in it. So our final answer when we added these together looked like this. It was x squared plus 3x minus 1. So this is still a parabola. So when we added the parabola function and the linear function, we still ended up with a quadratic, which is a parabola function. You'll notice though when we multiplied, so when we multiplied these two functions, we ended up with x cubed minus 3x minus 2. Same two functions, we had a parabola and a line to start out with. When we multiplied those, we ended up with this curve here. This is a cubic function. Cubic functions turn like this, all right, when they have something in between it. And the reason is because the degree went up. When we just added, the degree doesn't change. When you add or subtract, degree will not change. But When you multiply or divide, you are potentially changing the degree of your final function, right? And so this actually changed my degree. I went from the highest degree being squared, which is a parabola, to the highest degree now being cubic. So it actually changed the function and actually the shape of the function when we multiplied. And so that can happen when we multiply and divide. All right, let's look at one more function operation called composition. All right, so composition is different than the other ones. For the other ones, we basically had one function over here and one function over here, and then we did something to the answers. You can add, subtract, multiply, divide the answers if you want to. For composite function, you're actually inputting to one function, and then you're taking that answer and you're putting the answer in the next function. All right. The definition here is the composition of two functions f and g is denoted with this little open circle. Don't confuse it with the multiplication. This is an open circle. It's defined of f of g of x, or you can have it written like this where the function is inside the other function, and it is read f of g of x, all right? Meaning we have a function of a variable, all right? And so you're taking the input, output becomes the input of the next function, all right? And so there's two ways that we can do this. We can do this when we have an actual number, and you can input the function, get the answer, input that answer into the next function. Or we have it where it's a variable and you just come up with the new function that represents all of your answers there. So if you look at example 2 on page 334, we have evaluating with numbers first, okay? So when you evaluate with just a number, there are two ways to do it. You can do the composite piece first, or you can do the number piece first. So we're going to do it with the number piece because the next one actually has us doing the composite without numbers. So let's look at this first one. It says f of g of 2, negative 2. So we're going to take that negative 2 and we're going to put it into our g function first. All right, so we're going to find our g function. Our g function is 2x plus 1. So we are going to take that negative 2 and we are going to plug it into our g function first. All right. So we have negative 2 times 2 plus 1, we get a negative 3. Now we're going to take our negative 3 and we're going to plug it into our f function. So we're going to take this function and we're going to plug in a negative 3 for it. So we have negative 3 squared minus 3. Negative 3 squared is 9. 9 minus 3 is 6. So our answer to f of g of negative 2 is going to be 6. That is our final answer for that one. So if you have a number, you're just going to work from the number back. So the order is always going to be the 3 goes into this one first, and then that answer goes into this guy. So you work backwards. Work from the right to the left. All right, let's look at the next two. And this actually answers the question, does order matter? Because you'll notice for the next two examples, I have f of g of 3 and then g of f of 3. And so if I start here, I'm going to put the 3 into the g first. So I'm going to say 2 times 3 plus 1. So I have 2 times 3 plus 1, that's going to be 7. I'm going to take that 7 and I'm going to put it into my f function. So that's 7 squared minus 3. So I have 49 minus 3. I get 46 as my f of g of 3. If I do it the other way, 3 into f first. F of 3 is what I'm starting with. 3 squared minus 3. That's 9 minus 3. That's going to give me a 6. If I take that 6 and plug it into the g, I'm going to get 2 times 6 plus 1. 2 times 6 plus 1. G of f of 3 is going to be 13. So order matters with composition. You have to do it in the correct order. All right? If you don't, you will get a different answer. Sometimes they will say, all right, I want you to do f of g of just x. I don't want you to plug anything in. I want a new function that represents all values for the composite of f of g. And so when they give you something like this, you are going to take this function and you are going to put it into the first function. So I'm going to take all of this function and I'm going to plug it into the x for my first function. So I'm going to say, instead of x squared minus 3, I'm going to fill that in with my g function. 2 plus 1 squared minus 3. You plug in the entire function in for the variable. And again, you go left to right. So the g function in this case goes into the f function. The g function goes into the f function. And then you simplify it. This is just foiling. You're going to FOIL 4x squared plus 2x plus 2x plus 1, and then we have that minus 3. And then we simplify 4x squared plus 4x minus 2. So this represents all values for f of g of x, all right? Had they told us to do this, g of f of x, then I would have taken my f function now is going to go into my g function. So I'm going to take this function here and I'm going to plug it in for my x there. Always go this function into that function. So I'm going to say 2x plus 1. But instead of my x, I'm going to write my f function. 2. My f function is x squared minus 3 plus 1. All right? I'm just plugging in the entire function in to the other function. That is composite. And then I'm going to simplify. Distribute 2x squared minus 6 plus 1. Simplify this to x squared minus 5. That represents all of my values of my composite the other direction. Okay? So you take the second function and plug it into the first function. Another thing to say here, if they had done like f, we did f of g of 3, right? You could plug a 3 into here and get that same answer that you did as plugging in the 3, taking the answer and plugging that in, okay? You can get the final function and then plug the number in and it'll give it to you the final answer without having to do it twice. So, but we're about to do an example, so I want you to actually do these next 3. So for this first one, they do not want you to find an actual value. They want you to find a new function that has an x in it. For these, they want you to find the answer, a numeric answer, okay? And this is a little bit different here. You're going to plug 2 into g, take that answer, and plug it into g again. All right, so you can do a composite on itself as well. So do these 3. This is a new function with variables. This is 2 different directions for the same number, and this is a composite on the function itself. All right, so it says find its composite function and state its domain. State its domain. So if I want f of g, and they've given me the function in terms of ordered pairs, then I'm going to take each of my g's and I'm going to put that into my f function. So I have, for example here, I'm actually taking the outputs and putting it into the function. So if I look at my g function, this is my input of my g, but remember if I'm doing composite, I input the 1, the output is the 2. So I'm going to say, well, if I want f of g of the 1, then I would say, what's the output of the 1? Well, that's 2. And then I'm going to come over here and say, what happens when I put a 2 in for f? Well, when I put a 2 in for f, I get an output of 3. And so you're kind of tracking along. If I want f of g of 1, I'm going to look at the 1 under g and say, what is my output? My output is a 2. And then I'm going to take that 2 and plug it in here. Oh, there's my 2. What's my output here? That would be 3. And so you're just following the numbers along. So if I did the same thing for f of g of 2. Well, for f of g of 2, I am going to look for 2 again in my g. Well, for 2 here, my output is 0. Now I'm going to take the 0 and go over to my f and say, where's my 0? Oh, there it is. What's my output? My output is 1. So that's what composite does. It takes the output of one function, that becomes the input of the next function. All right? And so that's all they're doing with these. They're just finding it in the first and moving to the second one. So let's try this one. Evaluate the expression. They want f of g of 3. So start with your g, find your output, use that output to figure out which f you're looking for. So when we do composite, just like when we did addition, subtraction, multiplication, and division, we do have to consider the domain. So we do have to say, what is the domain going to be if I do this composite? And we have to look at the domain at the beginning and at the end, all right? And so if I look at the beginning, I am going to say, well, in the beginning, I can't have x equals 0. But what happens when I actually do a composite? How is that going to change? And so I'm going to do it in the order that they gave me. They want f of g. So I'm going to take f of g, putting g in for f. And then they want me to figure out, are there any domain issues when I do that? All right. So remember, the g goes into the f. So I'm going to rewrite my function. 1 over, and instead of x squared, I'm going to put my g in there. Square root of x minus 3 squared. Well, what happens when I square a square root? My root just goes away. We just did that, right? So this is my composite function. 0 is no longer a problem, but I do have another problem. 3 is a problem. And so I had a problem here. Here, x could not equal 0. I have a problem here. What's my problem here if I'm talking about real numbers? So for 1 over x squared, this was my domain issue. What about for square root of x minus 3? What's my domain issue when I have a square root if I'm talking about real numbers? I cannot have a negative, right? So that means we have to figure out where this is greater than or equal to 0, right? Because if it's less than 0, that means it's negative. So inside of my square root must be greater than or equal to 0. Well, we know how to solve that. We've done inequalities. So that means x must be greater than or equal to 3. That is my limitation here. X is greater than or equal to 3, right? So x is greater than or equal to 3. That actually takes care of this problem. Why? Well, if x is greater than or equal to 3, that will automatically exclude 0, right? So I don't even have to list this guy. He's taken care of right here. So now I need to look at this. What would cause a problem here? Well, 0 in the denominator. What's going to cause a 0 in the denominator? If it equals 3. So this cannot equal 3. So when I combine this domain, and that domain, I can just write it as x must be greater than 3. That is my domain. And so my answer is 1 over x minus 3. My domain is x has to be greater than 3. Okay? So I have to look at all of them, the original ones and the final, and it has to include all of those limitations. But in this case, one eliminated the other as I went. Okay? So you just have to write the final, what includes all of them. All right, questions on domain. Domain is really just saying, hey, it can be any number unless I tell you about a limitation. And if there's a limitation, I'm going to list that limitation and what it is. All right? Questions on that. Last one is a word problem. All right, let's look at this word problem and then we will be done. Addison has a $15 coupon for an electronics store and also receives an 8% discount as a preferred customer. Write cost functions modeling the effect of both the coupon and the discount on the price she pays. Then write separate composition functions modeling each possibility, order of applying the reductions. Use the composite functions to determine which order results in the lower price when she purchases a $200 wireless device. Okay, so we have two things going on. The first cost function that we're going to look at is her coupon. So we'll just label that with a C. That will be our coupon function. Her coupon is $15 off. So if the normal price is X, what's her new price going to be? Well, that's X minus 15. Yeah. Okay. So then let's look at her discount. We have a discount function that could happen. If X is the price and her discount is 8%, what is she actually paying for it? What percentage is she paying for it if she gets 8% off? 8% off? What percent is she paying for? Percent is 92%. So yes, we would write it as 0.92, right? So the percent off would be 92% is what she's paying for it. We always write that as a decimal. So we would write that as 0.92 for the function itself. Make sense? Because that's the percent. All right. So these are the two discounts. What they want us to do is they want us to say, which is going to be cheaper? Is it going to be cheaper if they do the dollar off and then the percent, or the percent off and then the dollar? So that is a composite function. That's what it is. And so we have two options here. We can say, well, we can do the coupon first and then the discount. That's going to look like that. Well, what does that look like for us? We're going to take this function and plug it into this. So we're going to say 0.92 times x minus 15. All right. And if you distribute, you get 0.92x minus 13.8. The other thing that could happen is we could say, well, we're going to do the discount first and then the coupon. What does that look like? We're going to take this and plug it in there. That looks like this, 0.92x minus 15. All right. Hopefully without even plugging it in, you can figure out which is going to be cheaper, right? The second one should be cheaper, right? So if we plug in a 200 for this one right here, the coupon first, and then the discount, we are going to get a price of $170.20. If we do the discount first and then the coupon, we will get a price of $169, right? So it actually matters. Order in which they apply things matter, okay? Now, if it were both multiplication, it wouldn't matter, right? But it does if it's a dollar off and then a multiplication. So car dealership offers two purchase options, $3,000 discount with an additional 3% off after the discount, or 5% discount off the full price with a $1,000 rebate applied after the discount. So set up two functions there. So for this one, the first option, the discount is 3,000 off the price. If the price is X, we subtract 3,000. The percentage is 3% off, so that's 0.97 times X. They specifically say 3% off after the discount, all right? Which means the discount goes first and then the percentage off. So this is the order that you would do it in. Discount first, remember that goes on the inside, then percentage. So we would take the discount and we would plug it into the X, and then we would distribute that 0.97, which is where we get 0.97X minus 2910. For the second one, we have a percent off at 5%, so that's 0.95. And then $1,000 rebate, that's minus 1,000. But then they say the rebate is applied after the discount. So that means that the 5% goes first, and then the rebate is applied. So percent first, then rebate. So you're going to take the percent then and plug it in, which is where we get the 0.95x minus 1,000. So these are my two options.